In this lecture we will learn about some properties of intervals, then we will move to the concept of nested intervals, nested interval property, nested interval theorem, and using it we will prove that set R of real numbers is uncountable. So let us recall, in the last lecture we have already discussed that suppose if a and b are two real numbers and we want to show that a is equal to b, so we can rewrite this statement as that if for every epsilon greater than 0 absolute value of a minus b is less than epsilon, this implies a equal to b, and already I have discussed the proof of this one. Why just recall this one, that if this absolute value, since this absolute value has to be less than each epsilon positive, so only option left with this is it has to be 0, that is a minus b has to be 0, and we have a equal to b, and we have already done its proof in the earlier lecture. Another important property we have covered is Archimedean property of real numbers, and as per Archimedean property of real numbers, for every xy belonging to R with x greater than 0, there exists at least one natural number such that nx will exceed y. And since this is true for each y, there is no restriction on y, restriction is only on x. So if I put y equal to 1 and x as epsilon, another real number, another notation for this real number x, then I can rewrite this statement as that for every epsilon positive there exists natural number n such that n epsilon exceeds 1 or 1 by n is less than epsilon. Now since we have order relation on set of real numbers, so we can talk of intervals. So the order relation on R determines a natural collection of subsets called intervals. This is the definition of open interval. Open interval is collection of all those x such that a is less than x less than b, that is all points in between a and b. Closed interval, in which apart from the points in between a and b, the boundary points a and b are also included. Similarly, this is the notation for empty set. One can write empty set as open interval AA, where A is any real number, because we are not including A, so we can write it as empty set. Similarly, singleton set, it can be denoted as closed interval A to A. So both of these, phi and singleton A, empty set, are considered to be non-trivial intervals. We will come to the proper definition of intervals. Length of interval is given by b minus a. If a equal to b, then in that case we will denote open interval a as empty set phi. So length of interval of, say, this notation I am taking for length of interval a comma b, and that is equal to b minus a. This is notation we are taking for length of interval, and length of a point is always 0. So length of open interval as well as closed interval or semi closed interval AB is b minus a. Another next property, the first set, okay, this is the notation for infinite closed interval. Here we can see that this is collection of all such x such that x exceeds a, x is greater than equal to a. Minus infinity b, this is collection of all such x where x is less than equal to b. And remember that minus infinity are not part of set of reals, they are just convenient symbols. Why? Because if in set form we will use to write R as collection of all those x such that minus infinity is less than x is less than infinity, or open interval minus infinity to infinity. Now 1 by 0 is always not defined, or 1 by 0 is undefined. The reason is that if 1 by 0 is defined, suppose 1 by 0 is infinity, then I can write 1 by infinity as 0, but infinity is not in our domain. We have open interval here at infinity. This is the reason why division in a non-zero number by 0 is not defined. Now let us do this characterization of intervals. So here suppose T is any real number. If we are claiming that S is a subset of R and it's an interval, then it has the property that whenever xy belonging to set S with x less than y, then the whole ray starting from x to y has to be contained into the set S. Or in other words, if x y belongs to set S and there is a, if x y belongs to set S and there is a real number T such that x is less than T is less than y, this implies T should also be in the set S, which we are claiming to be interval. For example, open interval say 1 to 4 union say 7 to 10 is union of interval but not an interval, is union of intervals but not an interval. Why? But not an interval. Because say from this I can choose x is equal to say 3 and from this I can, let me call this set as A, and y is equal to 8, both are member of the set A. In between 3 and 8 we have 5, but 5 is not in A, 5 is not in A. So if we have at least one element which is not member of the set and lying in between x and y, then we will say that this is not an interval. So union of interval in general need not be an interval. Now phi, empty set phi and singleton set A are trivially interval, because to discard that subset of R is not an interval, I need at least one T whenever x y belongs to S with x y different, x less than y, then in that case I need to have at least one real number T which is not member of the set S. So since phi has no two such elements, so there is no T which fills this definition, and the same is the reason for singleton A. So empty set and singleton set are called as trivial intervals. Trivial intervals. Other example of open set, we can take any continuous strip, continuous ray. For example, open interval AB, closed interval AB, semi closed interval, the intervals of the type minus infinity B. All these are examples of intervals. Next point, nested interval. So first of all, let us understand what we mean by sequence of nested intervals. Sequence, already I have discussed that a sequence is a mapping from a function from set of natural number to set of real number. So its domain is set of natural number. So I can do, because set of natural number, its domain is set of natural number. So we need to using set containment, using a chain of inclusions. Suppose if we have this interval in is contained, in plus 1 is contained to in and so on, then we will call such containment relation as sequence of intervals. For example, for in is equal to 0 to 1 by n, if we consider in is equal to 0 to 1 by n, then in that case I1 will be 0 to 1, I2 will be 0 to half and so on, I3 will be, I can write I3 as 0 to 1 by 3. Now clearly I3 is contained into I2 and I2 is contained into I1 in case in equal to 0 to 1 by n and so on. Why? Because every member of 0 to half, every real number from 0 to half is also member of this set I1. So this is the reason we have set containment. So if we have such sequence of set containment, we will call such it as sequence of nested intervals. So here what motivates us to study this nested interval property and nested interval theorem is that if such nesting is there, what can we say about their intersection? I mean, is there any member common to their intersection? What about their intersection? Or there are more than one members in their intersection or there is no member in their intersection, under what condition there will be at least one element in which is common to each of such interval, intervals. So this is what nested interval property. But before going to this, here if we consider in is equal to 0 to 1 by n, and let us take intersection of I1, intersection I2, I3, so on. So we will see that there is exactly one element which is common to all the intervals, that is 0, and we can write it as interval form in from n is equal to 1 to infinity, it as singleton 0. That is what written here, n equal to 1 to infinity, in is equal to singleton 0. This can be proved using Archimedean property of real number, that there is no other element greater than 0 which is common to each of the interval. If we consider Jn equal to open interval 0, 1 to 1 by n, then there is nesting, but to all such interval there is no point which is common to all such interval. Now here we have diagram. I1 is this interval. Okay. So there is here it is written that there is no common point there is nested, we have nested sequence of interval, but there is no common points to all such INs, say 0 to 1 by n open interval, and I need to look at its intersection, n is equal to 1 to infinity. So we need to claim that this is basically empty set. See, I1 is this interval 0 to 1, I2 is this interval 0 to 1 by 2, and so on. Now obviously if there is any member in I1, it will be strictly greater than 0. If again there is any member I2 in 0 to half, then again it is right to 0, so it has to be strictly greater than 0. So if there is any real number which is common to each of the interval, say x, then it has to be strictly greater than 0. Suppose there is some number which is common to each of the interval, say I1, I2, In, and so on, then it has to be strictly greater than 0. And whenever x is strictly greater than 0, I can apply Archimedean property of real number. So there exists n belonging to set of natural numbers such that 1 by n is less than x. I mean there will be suppose x is here, so there will be natural number n such that 1 by n will be strictly less than x, that is 1 by n is left to x. And what we are claiming here, that intersection of all such I1, I2, I1 is 0, 1, intersection 0 to half, intersection 0 to 1 by 3, and so on. So if there is any element which is common to each of such interval, then such x has to be less than 1, such x has to be less than half, such x has to be less than 1 by 3, and so on. That is, x has to be less than 1 by n for every n belonging to n, because it has to be in between the open interval 0 to 1, and the end point here though not included, but it is of the type 1 by n, 1, 1 by 2, 1 by 3, and so on. So if x is common to each of the interval, then x has to be less than 1 by n for every n belonging to n. This is because we have assumed that x is common to each of the interval, and also x has to be greater than 0. But from here, from this Archimedean property of real numbers, we have a contradiction. Archimedean property of R, Archimedean property of R, that there exists n such that 1 by n will be, there will be a moment such that 1 by n will be left to x, and here we are getting x left to 1 by n for every n. So this is the reason why such x greater than 0 is not possible. So that's what written here, that since for every x given x greater than 0, there exists m belonging to n such that 1 by m is less than x, so that x is not in all of the Jm. Similarly, the sequence of intervals kn equal to open interval n to infinity, again we can apply Archimedean property of real number to show that though there is a nesting of intervals of kn, but there is no common point to which is common to all such intervals. However, it is an important property of real numbers that every nested sequence of closed and bounded interval does have a common point. So, we have our answer to this, that under what condition there will be at least one element which will be common to all such nested intervals. So, if the sequence of interval, nesting of sequence of interval is of closed and bounded intervals, then as per nested interval property we have at least one element. So, that is the statement of nested interval property, that if in equal to an bn, where n belongs to n, is a nested sequence of closed and bounded interval. Bounded intervals means its length has to be finite, or we can say that the interval has to be contained into some diameter of finite length, or if there exists at least one upper bound and at least one lower bound, which we have already covered in our lecture on bounded and unbounded set. So, if we have, whenever we have nested sequence of closed and bounded intervals, then there exists at least one number. There exists a number means there exists at least one number which is common to each of the real numbers. Let us denote that real number by xi. So, this is the statement of. So, we need to have nested property, nested sequence of interval as well as closed and bounded. Then it is always guaranteed that there exists at least one point which is common to each of the interval. Otherwise, there may be point common or there may be no point common to such intersection, which we have already covered in open interval 0 to 1 by n, intersection of all such interval, and open interval n to infinity. So, bounded is also important, because this one is not bounded in open interval n to infinity, its length is not finite. Now, again question is that under what condition there is exactly one point common to all such intervals. So, that is called nested interval theorem, and as per theorem, if in equal to n bn is a nested sequence of closed and bounded intervals such that the length of bn minus an, that is the length, if infimum of this set is 0, infimum of their length is 0, then this number xi, which is common to all such intervals, will be unique. So, using this we will show that, for example, we have shown that closed interval 0 to 1 by n, closed interval 0 to 1 by n, its intersection from n is equal to 1 to infinity. This is exactly singleton 0, because though we have proved it using Archimedean property of real numbers, but it if we observe, it is also going to satisfy this theorem. Why? Because infimum of the length, this is sequence of closed and bounded intervals, and also its infimum is 0. Why its infimum is 0? Because its length is 1 by n minus 0, that is infimum of the set 1 by n, and we know that infimum of 1 by n is 0. Why? Because if we write this set, it will be of the type, say, put n equal to 1 here, 1, 1 by 2, 1 by 3 and so on, 1 by 3 and so on. Infimum is among all lower bound, the greatest one is called infimum. Okay. So, every real number less than equal to 0, every real number less than equal to 0 is its lower bound, So, what will be set of all lower bound? Set of all lower bounds, that will be minus infinity to 0, including 0, because 0 is also one of its lower bound. Now, infimum is, as per definition, greatest lower bound. So, that of this set is 0. So, this is also satisfying this condition, this requirement. Hence, xi is the unique element, which is xi equal to singleton 0 is 0, is the unique element common to each such interval. Now, using it, we will do the proof of, we will show that set of real number is uncountable. Now recall what we mean by countable set. In my lectures on countable set from Rudin, I have discussed that a set is said to be countable as per definition of Rudin. Any set A is said to be countable if we have at least one bijective map between n and the given set, at least one to one correspondence between set of natural number and set of A, the set which we are claiming to be countable, Now we need to show that using nested interval property that the set R of real number is not countable. So what will be the algorithm to do it is that on contradiction we will assume that the given set is countable, and since it is countable and we know that every countable set is in bijection with set of natural number, so we can enlist, we can enumerate, we can exhaust every member of the set with the set of natural number or indices of natural number, that is say x1, x2, xn or a1, a2, n, whatever enumeration we are taking, and there should be no element left because we have enumerated it with the set of natural number, it is in bijective correspondence with the set of natural number. And later on we will claim that we will construct another element which is from this set but not counted with the set of natural number with this enumeration. So that will be our algo, and that way we will claim using the nested interval property. So just go through this proof. I need to show that the set R of real number is not countable. We will prove, and again, since in nested interval lemma, if you recall, then we have the condition that there should be nesting of sequence of closed and bounded intervals, So we will start from closed intervals, and also because R is not bounded, set of real number is not bounded, so we will start from its sub interval closed interval 0 1, because if sub interval closed interval 0 1 is uncountable, then its superset has to be uncountable, and the advantage with closed interval 0 1 is that its length is 1 and it is bounded, it is bounded above as well as bounded below. So we will prove that unit interval is an uncountable set. This implies that set R is an uncountable set. Okay. So the proof is by contradiction. If we assume that I is countable, then we can enumeration only we can do with countable set. So suppose the members of set real, because we have assumed it as countable, it is denoted by x1, x2, xn and so on. Now let us select a closed sub interval I1 of I such that x1 is not in I1. We need closed here. Why? Because we need to apply nested interval sequence. So closed, it's already bounded because we are denoting the members of this closed interval 0 1 by I, that is x1, x2, xn and so on. In this way we obtain a non-empty closed intervals. Again select I2, the sub interval of I1 such that x2 is not in I2. Continue this process. Now each of the set Y it's non-empty because x1 is not in I1, but other elements x2 onwards are in I1. Similarly in I2 x1 and x2 are not, the x2 is not there, but other elements other than x2 are in I2, x1, x2 are in I2. So this is a non-empty, and already we have started with closed sub intervals. So there is a nesting I2 contained to I1 and so on. So the requirement of nesting closed and bounded intervals is complete here, such that in plus 1 in is contained into I, each of the in is contained into I is this one, x1, x2, xn and so on, and xn is not in in for all n. Now as per nested interval property, since we have a nesting here of sequence of closed and bounded intervals, there will be a element xi which is common to each of the interval in. There will be at least one real number because it is fulfilling the nested interval property. So there will be a real number xi which is common to each of the interval in. So this xi has to be different from x and y. This xi has to, because this xi is common to each of the interval, whereas xn has the property that x1 is not in I1, x2 is not in I2, x2 is not in I2, and similarly xn is not in 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 general for all n. Thus, we have constructed a new element xi apart from this x1, x2, xn, x1, x2, xn, which is not exhausted with the listing with set of natural number with this enumeration. That is what written here, that the nested interval property 2.5.2 implies that there exists a point xi such that xi belongs to In for all n, therefore xi is not equal to xn for all n, it is different, and thus our enumeration with set of natural number is not complete. This means that our claim that I is countable is not true. On contrary to it, the closed interval 0 1 is uncountable, and since closed interval 0 1 is uncountable, so its superset has to be uncountable. So, this is the very good proof using nested interval property. We will do it again using that real number representation technique in binary or ternary or decimal form. I will come back to that method also. Now, there is another property, just we need to recall this property. The fact that set R of real numbers is uncountable, and we can write R as union of rational as well as irrational, R minus Q, that is notation for irrational. We know that Q is countable whereas R is uncountable, and union of countable set is countable, countable union of countable set is countable. This means a set of irrational has to be uncountable, otherwise their union will make R to be countable, which is not true. So, thus we have proved that the set irrational is an uncountable set. So, R is being classified into rational as well as irrational, union of rational and irrational. There is another classification into algebraic and transcendental number. Just I want to recall the definition here, that any real number is called algebraic if it is solution of a polynomial equation with integral coefficient, with coefficient as integer. So, all those are, for example, x equal to root 2. If I put x square minus 2 equal to 0, then its coefficient 1 and minus 2 here are integers. So, root 2 is an algebraic number, root 2 is an algebraic number, whereas e pi are transcendental number, those number which are not solution to a polynomial equation, those are called as transcendental number. So, real number can be classified as union of algebraic set of algebraic number, union transcendental. Again, set of algebraic number is, I am not going to discuss proof here, but set of algebraic number has been proved to be countable, whereas set of transcendental numbers is uncountable. So, this is another way of looking the real numbers into rational, irrational as well as into algebraic and transcendental number. In next lecture, I will cover the binary representation, how to write any given number into binary, ternary and decimal form, and then from there we will do this theorem. After decimal representation, binary and ternary form, we will do this theorem, the unit interval 0 1 is not countable using the representation of real numbers, and then we will move to the concept of Cantor set.